Hello everyone, welcome to a new video. In today's lecture, we're gonna discuss what are ensembles and random forests. Okay, so far in the models that you have learned for classification and regression, typically we use a single model to make a prediction. Now, the key idea of ensembles is why using just one opinion if you can get multiple opinions. So the key idea here is to get the wisdom of the crowd. So instead of relying on a single model, let's use multiple models to make the prediction. So if it's a regression, we're gonna compute the average of the different models. If it's classification, we're gonna vote. We're gonna the majority vote. So the whole idea is that when you have your data, you can split the data, take some data, do some sampling, and train different models. They can be, let's say if this is a classification problem, you can use logistic regression, SVM, random forest, XGBoost, different techniques, neural networks, right? And each model then will make a prediction, like here in this figure. So you have here 4 different models, right? You have diverse predictors, and each of them will make a prediction. So the first one is saying, okay, class 1, the third one, class 2, and class 1. So 3 models said class 1, and a single model said class 2. Therefore, the majority vote is 1. So that will be the ensemble's prediction. So the idea behind this is just let's create something more robust by using multiple models. And that's true. Because even if you have some weak learners, and by weak learners means that models that have just like slightly that are slightly better than just tossing a coin, they get way better when they are combined with other models. The results are better. So in general, when you do ensembles, you will improve or keep the performance, but it's going to be weird that, generally it won't drop. Okay, so there are different techniques or ideas. The first one is bagging. So in bagging, the key concept is, okay, we are our training data, and we bootstrap samples from the training data. That means that we sample with replacement. So we start sampling and we start getting different learners or different models, right? And each of these models will classify or will make regressions. And we were going to combine, if it's a classifier, we're going to use the majority vote. If it's a regression, we're going to compute the average. And this Bayesian idea, we expect that it's going to reduce variance. That's the main advantage when we apply this concept of bagging. In random forest, it's a combination. It has bagging, but it also has a difference. So in random forest, this is an ensemble. The name indicates that instead of using a single tree, we have like multiple trees, n trees in general. In scikit-learn, the default is the n estimators parameter. The default is 100 trees, but of course you can change how many trees you want to create. Now, in order to avoid, like creating the same tree several times, so the strategy here for the random forest is that from your training data, it's going to perform some bagging. It means that it's going to make samples with replacement, but on top of that, it's going to do some future sampling. It means that, let's say that you have 20 variables or 20 futures, it won't use the 20 of them for every single tree. It will pick a sample, and that's a hyperparameter that you can define how many futures you want to pick out of the 20 or the total that you have. So by like randomizing the sample and also the number of futures, it will create different trees. And you have diversity, which is the main idea behind these ensembles, to have diversities in the opinions and predictions, so we get a more reliable prediction. A second key concept which is different than bagging, is boosting. So in bagging, we have like models in parallel, and they are kind of like disconnected, let's say. But here, when you perform boosting, we create our models sequentially. So it's like iterations. So for example, here we have our data, our original data, our training set. So we train our first model, as you will train any other model. And then the boosting idea means that you're gonna keep improving that model. So the next model, model 2, is gonna be based on the errors from model 1. So once you train model 2, then for model 3, you will try to improve the errors from the previous model. So it's sequential. There's a sequence here, and we're trying to improve the performance. That doesn't mean that we're going to use just the last model. We're going to use all of them. We're going to use all of them. But the difference that this is they are created sequentially. It's not in parallel as the bagging strategy. There are different algorithms here for boosting. So we have gradient boosting, ARA boost, XG boost, which is the extreme gradient boosting. I would say right now it's like the most popular boosting algorithm for sure, the XG boost, because it's powerful, scalable, it has good performance with tabular data. It's one of the best algorithms for regression and classification. Other alternatives are like GVM, CAT boost. This one is specialized when you have categorical variables. Okay, so in gradient boosting, when we're going from one model to the next one, for the first model, model number 1, we train, okay, we use the X variables and the Y variable. But for the next models, for the second one, for example, we don't use the original Y. What we use is the residuals or the errors from the previous model, from model 1. So for model 3, you will use the errors or residuals from model 2. So you try to improve improve the residuals by making the predictions over the residuals. It's like learning from the errors of the previous models. Now we call these models or these algorithms gradient boosting because they optimize, using gradient descent. So that's why we call them gradient boosting. At every iteration, they are optimizing the performance of the model, training over the errors in order to minimize the error. So regularization here is really important in order to avoid overfitting. And as I mentioned before, XGBoost is by far the most popular algorithm in this category. This is a very nice idea, stacking. So far, when we talk about ensembles, regardless if we talk about bagging or boosting, at the end we have like multiple models, right? We make predictions, and then we just mention like 2 basic rules. If it's regression, we compute the average of the models. If it's classification, it's like a vote, and we pick the majority vote, right? So we blend the prediction just using these 2 rules. Now in stacking, the key idea is why using a basic rule if you can use a model to do the blending. So we can train a model here on top of these models. So the outputs from the original models, these y-hats, these predictions, it will fit our blending model, and our blending model is going to try to use them to make a better prediction of the original y variable. So that's the idea of stacking. So it's an ensemble technique that learns how to combine the predictions of multiple models. Now, this is a powerful idea because we can add layers in the models. So it's not just having like a single layer with multiple models and a blending. We can add more layers here. This is the multi-layer stacking. So instead of having a single layer with multiple models, why not use these inputs with different algorithms here, here, and here, right? And then we have another layer to combine these outputs to make the final prediction. So this is very powerful because even though, of course, there are some computational cost for this. You will need more resources, but also if you control the regularization of the algorithms and you can generalize, it's possible that these models will improve bias and variance. They are going to be more powerful. Actually, they kind of like mimic neural networks. Neural networks, they have these ideas. They have like multiple models that at different layers, and the outputs of one layer will be the inputs of the next layer. So, and neural networks are really powerful with unstructured data, but we can mimic that behavior also here with multi-layer stacking, where we can have here different algorithms. Let's say you can create here a logistic regression with a tree, and then you can have here XGBoost. And same here, you can have different algorithms, right? In the end, you blend all these outputs into a single one, right? To make the prediction. So this is a nice idea that we'll be testing during these upcoming weeks. Okay, so in conclusion, ensemble methods, they are powerful. Typically, when you want to make good predictions with the high accuracy, ensemble for sure will be present in different ways. Random forest, boosting, for sure will be there, or at least some models based on these ideas will be tested when we are comparing algorithms. In bagging, it's going to focus on reducing variance, right? While boosting is going to reduce bias. So they have the different idea. In the case of stacking, it gets the you can get buy-in and boosting because you can combine models here. So the stacking it's more flexible. Potentially, you can get better models if you do stacking. However, there is a cost, right? In stacking and also in ensembles in general, they come with a cost because you will need to compute not just a single model but multiple models. So it's going to increase the computational complexity, also the interpretability. If you have like stacking with multiple models, multiple layers, then interpretability can be an issue. Now, if your main focus in the context of application that you are dealing with is about accuracy, like low error, high quality predictions, then stacking may be a good idea. All right. Okay, I'm gonna stop the video for now. I hope to see you in our next lecture.